6.3, we're talking about vectors. So we did law of sines and cosines the past few weeks. And those are kind of one part. This whole chapter, this law of sines and cosines are kind of one little subsection. And then the last 3 sections are all about vectors. So you're going to learn all about different vectors. So yes, so we talked a little bit about vectors on Monday, right? We have how we name a vector. So this would be vector PQ. And then if we want to talk about the magnitude of the vector, we use these double lines, kind of looks like double absolute value, right? And that actually gives us the magnitude or the length if you think about a vector. And then on Monday, we talked a little bit. Oh yeah, Jennifer says they kept hitting the flag. They did. With quite a amount of force, they hit the flag. On Monday, we also talked a little bit where we started with this is how can we add vectors together? So you'll see here, if you have U as a vector, U1 and U2, and V as a vector, V1 and V2, if we add the 2 vectors together, then we're basically adding, it's kind of like the X component. We don't call it the X component, but we're adding the first component of our vector to the second to form our new vector. And then we're adding the second, the Y, to the second value. So we'll do some of these to see this. We can also multiply by a scalar. So if we have a vector U and we multiply it by some constant K, then we basically are going to multiply that constant K by each value in the vector. Okay. And so you might have heard the scalar multiple and the sum before when you did matrices in Algebra 2. Did anyone do matrix addition and multiplication, scalar multiplication? Yep. Okay. So you probably have heard this terminology before, and this is the same. So this idea of vector addition and scalar multiplication is the same with matrix addition and scalar multiplication with matrices. And spoiler alert, when we get to 6.4, there's a special way that you multiply vectors together. You don't just multiply the first terms and the second terms. Okay. And then down here, there's a couple properties of addition and scalar multiplication. So these all should feel pretty familiar to you. We have that, if you have U plus V, that equals V plus U. So you can add vectors in either order. You have, if you add a vector to plus 0, you're going to get the vector. If you multiply by 2 different scalars, you can multiply the scalars together first and then apply it. I'm kind of going out of order here. Sorry, I just realized that. Number 7 is if you have a scalar times 2 vectors that are added together, you can use the distributive property, and you can distribute that scalar to each vector. This one, number 9, is kind of an interesting one. We use this a little bit. If you have a scalar times a vector and you want to find the magnitude, you can pull out that scalar and find the vector separately. Over here, I should have been doing this order. Number 2, if you have, what is this? The associative property. If you have U plus V in parentheses plus W, then you can, rework the way you're adding. If you have U, vector U plus negative vector U, you get 0. This is kind of the reverse distributive property that we talked about. And then 1 times a vector U equals U, and 0 times a vector U equals 0. So I think there's nothing shocking or kind of new in that. Okay. And then we'll talk about unit vectors in just a minute when we get to some more work. So that's kind of a bring your brain back to what a vector is. On Monday, we left off, I believe, let's see. On Monday, we left off doing number 18, I think was the last one we did. So what we just had kind of started talking about was, oh yeah, we were right in here. What we had just started talking about was how do we add and subtract vectors together, and what does that actually look like when you have the vector plotted out? So let me first of all make this screen a little bigger. Maybe. That's what I want to do. Okay. And good morning, Sarah. I didn't say hi to you. Good morning. My computer is going slow this morning. It was up too late watching the Olympics too, I guess. Okay, so we kind of did this in class on Monday. We actually did, I think we did example number, where are we at? We did 14 through 18. So this is kind of the same thing. We have some vectors here, and we want to actually look at the vectors and try to figure out where these new vectors would lie in our coordinate plane. So you can see this is graphed on an x and y coordinate plane. We have vector u that is going down, you know, in your fourth quadrant down here, and vector v that's going up in your first quadrant. So number 20, they want us to figure out what would negative 3v look like. Okay, so negative 3v, kind of break this down, because we know, this is going to be fun to do online, because we know we have vector v right here, we know a negative vector is going to go in the opposite direction. So it's going to go like this. Okay, so this would just be negative v, because that's the vector in the opposite direction of v. But we have negative 3v, so we don't not only have one of these, we have two more that we need to add on. So another one and another one. Well, that there-ish. So this would be negative 3v. Okay. If you wanted to do half v, I think you can figure that out. That would just be half your line. Okay. And then number 24, what if we have 2u plus 3v added together? How do we figure out where those go to? So what you want to do is you have, start with one of them. So let's start with 2u. So we have u here. Okay. And if we put another one on, that's 2u. Right? And then we're adding 3v onto the end. So v is going in this direction and it is this magnitude. So we're ending up here. Here's 2u. We want to go up 1v and then another v and then another v. So I have 2u and then plus 3v, and my vector would end up, that's not exactly where I drew it, but you get the idea. It would end up out here, right? This would be 2u plus 3v. Gonna end up out this way. Okay, so that is vector addition and subtraction on a graph and scalar multiplication. Any questions about that? Is that all right? Okay. Then we have I'm sorry. Then we have this next problem here. So we have number 26 and 28. And then when we get to 30, you can see that this looks totally different, and we'll kind of talk about what that looks like. So number 26, we'll kind of go through fast. We have vector u and v, and we want to find out what happens when we add the vectors, subtract the vectors. We have 2u minus 3v, and we have v plus 4u. So this is just kind of a math problem to kind of make sure that we know how we add and subtract. So we have vector u equals 5, 3. Vector v equals negative 4, 0. Okay. If I wanted to add u plus v, you're basically going to be adding in my math mind, I think of this as my x and a y. So you're basically going to be adding the x and the y. So you're going to be adding 5 plus -4. And then you're going to add 3 plus 0. And you get u plus v equals 1, 3. So if we graphed these, right, if we graph these on a plane, we should end up in the same spot. I'm not going to make you watch me graph it out. But if you graphed u at 5, 3, so that's going to be in the first quadrant. And if you graphed v, which is -4, 0, right, over here, that's actually going to be on the x-axis. And then if you take those and you combine them together, you're actually going to end up still in the first quadrant. So that seems reasonable. Okay, b, same way, except we are just going to subtract, right? So we would do u minus v equals 5 minus a -4 and 3 minus 0. So we get 1, 0, that's a 0, 1, 3. Okay. See if we have 2u minus 3v. So we have two different scalars that we're multiplying by. Okay. Yeah, we have two different scalars that we're multiplying by. So I would go ahead and multiply each scalar first. So what I mean by that is I'm going to do 2 times u, which is 5, 3. Well, yeah, you definitely want to do that first. Minus 3 times -4, 0. And just like with the distributive property, well, we have, oh yes. Thank you, Aiden. Or Jennifer. I was thinking it was Aiden because Aiden always corrects my math. Yes, thank you, Jennifer. Yes, that should be 9. All right, so here we're going to go 10, 6, right? And then I'm going to go ahead and make this add a -3 so that I don't have to worry about that. So -3 times -4 is +12. -3 times 0 is 0. So then I can just add my terms together to get 22 and 6. All right. I don't even think you guys need to see D. I think as long as you add and subtract correctly, those should be easy peasy, right? Any questions about that? All right. Pretty easy. Okay, so now we're going to talk about, we talked about how we can write vectors, right, with the component form and different ways we can write it. We're going to actually talk about how we can write vectors in another format, and that's using the letters I and J. All right, so let me clear this off so we have a spot. Okay, so we have these two unit vectors. We have I, if it will let me write it. I is a unit vector that's represented by 1, 0. And we have J is a unit vector that is represented by 0, 1. Okay, so these are standard unit vectors. And this I I don't know why they picked I, because we have the imaginary number I. This I is not the imaginary number I. So in the book, I think they say that they bold this I and this J when they're talking about vectors versus just a fancy I when they're talking about imaginary number I. So this I is not the imaginary number. It is a different I that we get to use in math. All right, so these are standard unit vectors, okay? And so if we have a vector that's written in this format, we have the horizontal and vertical components, basically the x and the y. So we have a vector v1, v2. Okay, so I'm going to do one off to the side that's some real numbers so that you can basically see. Or say our vector was like the last problem. It was at 5, 3. This is one way that we can write our vector. Another way that we can write our vector is by using these unit vectors to represent the distance, and then we have a scalar that we're multiplying by it. Okay, so what I mean by that is that we can actually say, and your book does a good job of kind of breaking this down, but we can actually take the number part of our vector, our first vector, so v1, okay, and we can multiply it by 1, 0. This is like our unit vector. Okay, and so what this does, these equal each other because if you multiply this out, this is basically v1, 0, right? It's the vector in the horizontal or the x position. Okay, and then for the second one, we can also write this as a scalar number, v2, times the unit vector 0, -1. So now if I translate this, and instead of writing this as my unit vector, I write v1 times I, got to make my boldface I, plus v2 times j. So now we have scalar times a unit vector, scalar times a unit vector. So what this looks like with a real example, like 5, 3 over here, if I make my screen a little bigger. So we could rewrite the vector 5, 3 as 5 times the unit vector I plus 3 times the unit vector j. And these are equivalent vectors to each other. It's just another way of writing it. The benefit of writing it in terms of unit vectors is that if you want to do vector addition and subtraction, it's kind of easier because we use these like a variable, and then we kind of are able to add and subtract quickly. So you'll see this is a very common terminology, this unit vector terminology. So if you see I and J, they might not be talking about imaginary numbers. They might be talking about, they're probably talking about a vector. Okay, so how does that work if you, for example, number 30, they've given us 2 vectors, and they've given us this in by representing it as unit vectors. So we have u equals 2i minus j, and v equals -i plus j. All right, so just to kind of, that's what I was trying to do, just to kind of wrap it all together. Another way, that's not what I was trying to do. Erase this and then I'll tell you. Okay, so another way that you could write, so we're at number 30 here. Another way that you could write u would be, a vector u would be 2, -1. Okay, so basically you're just taking out, you're taking the size of it, right? And you're multiplying it by unit vector. Okay, and so another way we could write v is -1 positive 1. Those are equivalent vectors to each other. Kind of the somewhat of an advantage, especially if you get into more complex vectors that have more. So you can have, right now we're working with 2D vectors, but if you have a 3-dimensional vector, that can get a little bit easier for you. So if we wanted to, for example, add u plus v, okay, then we can just add 2i minus j plus negative I plus j. Okay, and then you're going to treat these unit vectors just like you would treat a variable, right? So we have 2i minus I, so we have I. And I've got to stop writing I like imaginary number. And then we have minus j plus j, so that's 0. So u plus v is just I, or vector 1, 0 by definition. Okay, u minus v would be 2i minus j minus negative I plus j. All right, make sure we distribute our negative. So we got plus I minus j. So you end up with 3i minus 2j. Or if you wanted to write that in component form, you can write 3 negative 2. Okay. Where it might make it a little easier is when you're doing like example number or C, right? Where you have, I have to make my paper longer, 2 times u minus 3 times v. I don't know. I don't know if it's easier or not, but just different. So if we have 2 times u minus 3 times v, right? We can do 2 times 2i minus j minus 3 times negative I plus j. And again, I'm going to just go ahead and put my negative on my 3 so that when I distribute, I can just add after that. So I have 2 times 2i, 4i minus 2j. And then I have negative 3 times negative I, so positive 3i minus 3j. And I end up with 7i minus 5j. Or 5 or 7 negative 5. So not hard, just kind of a different way of looking at things, I think. Any questions about that? Nope. Cool. It's exciting stuff, right? Okay, so I was looking at number 30. I'm looking at number 31 through 34. So you should probably look at that really fast. And then we have kind of a new thing to talk about. So it says in exercise 31 through 34, use the figure and write the vector in terms of the other 2 vectors. So what they've kind of sketched out here is that we have, for example, not for example, on the picture, you can see that you have vector u plus vector v equals vector w. Okay, So can you kind of see that on there, what they've sketched out for you? So we have vector u plus vector v equals vector w. I'll just write that down. U plus v equals w. So they said use the figure and write the vector in terms of the other two vectors. So if I wanted to find what v would be, I'm just going to solve this equation for v and say that vector v equals vector w minus vector u. So that's all you have to do is kind of solve for that. 34 is slightly more tricky, but not too bad. So we have, what do we have if we have two vector v's? Okay, so what we want to say is what happens if we have two? Well, let's just multiply our original equation by 2, right? So we'll multiply this by 2 and multiply this by 2. And we end up with 2u plus 2v equals 2w. And subtract 2u from each side. And we get that 2v equals 2w minus 2u. Sorry, that's so messy. So basically, if we have two u's, we have two w's, 2 w's, and then we subtract 2 u's. So right now, positive u is going in that direction, right? Then we're going to end up with 2 v's. We're going to end up down here. So subtract 2u is going to look like this. And then we're going to end up with, I can't draw it on here. We're going to end up with negative 2v, or 2 v's. 2 v's in that direction. So that's how you're going to do that little section. Pretty easy. All right, so now that was kind of just a off the side thing. The last part of your notes, back up here. Unit vectors. So in many applications of vectors, it is useful to find a unit vector that has the same direction as the given non-zero vector v. To do this, you can divide vector v by its length to obtain a unit vector. So a unit vector is representative of the direction of the vector. So this formula is going to help us figure out a unit vector in the same direction so that we can basically multiply by a scalar of that vector. Okay, so let's kind of keep this in mind, what the definition of a unit vector is, or how we find a unit vector for any vector. And let's look at a couple problems so we can kind of visually see what that looks like. Okay, so let me pull that up here. Maybe. There we go. All right, so in 35 through 44, we're going to find a unit vector in the same direction of the given vector. So we already talked about the standard unit vectors, which are I and j, so 0 and 1 unit long. But we're going to find another unit vector in the same direction of our vector. So we have number 36, we have vector u is at 0, -2. Okay, so we want to find a unit vector that is in the same direction of this. So what we're going to do that is we're going to actually use this formula. So let me pull it up here. Copy. There we go. really big for us. Well, we'll get most of it on there. All right. So in this terminology, they've kind of overlapped u and u. But we have a vector u, and we want to find the unit vector. We're also calling it u. So let's kind of think of this as v, just so we don't confuse ourselves, right? We'll think of this as v. And we want to find the unit vector that is in the same direction. So this is basically just an exercise in finding the magnitude of your vector and then plugging it into here. So if you recall from Monday, also in your notes up at the top, right? When you go to the magnitude or the vector, right? The magnitude of a vector can be found as v1 squared plus v2 squared. And this is back from the component form. That's notes from that. So for this example, if we want to find the magnitude of vector v, we have, this is going to be a pretty easy one, right? We have 0 squared plus -2 squared. And so if we have basically -2 squared square root, we end up that the magnitude of v is 2, right? So then our unit vector is going to be our vector, which is 0, -2, divided by 2, or 0, -1. So I think this makes sense if you just think of this as a graph, right? Our original vector is at 0, -2, right? And our unit vector is basically -j. It's 0, -1 in that direction. So that was kind of an easy one to start, right? Let's get a little bit more complicated. Maybe. Okay, so let's try number 38. If you have your paper, you can try this out too. So 38, we have v, if I can write. I always forget to do that. We have v equals, our vector v is 3, -4. All right. So does anyone know what the magnitude or the length of this is going to be off the bat? Right, we're going to have 3 squared plus -4 squared. It's our good friend Pythagoras coming back again, right? 9 squared plus 16 squared, 25. So we get that the magnitude of this vector is 5. Yep, Jennifer got it, 5, right? So then if I want to come up with a unit vector that represents my vector, okay, it's going to be, my unit vector u is going to be 3, -4 divided by 5. So what that's going to look like is 3/5 -4/5 off the side there. That's going to be my unit vector. So why we consider this as a unit vector is if you combine the horizontal and vertical components of that, you're going to end up with a unit of 1, right? So for v is at 3, 1, 2, 3, -4. This was our unit, or this was our original vector v. And then our unit vector is at 3/5, -4/5. So it's just actually a little 1 unit vector that goes down here and that is in the direction of the given vector. Exactly, Aiden. So that's basically what we're trying to find. Any questions about that? Would you like to see another example? Yep, absolutely. I was just going to say that. Yep. And Aiden, just to bring that full circle, like what you just said. So Aiden said, so it's the same direction with a length of 1. You can prove that if you took 3/5 squared plus 4/5 squared, you're going to get 1 for a unit vector. So you're basically finding 1 unit vector in the same direction. All right, so let's do number 42. I forgot, I erased my... So number 42 is the same idea, but it's written already with our unit components. So we have W equals I, I'm so tempted to write the I like the imaginary number, sorry. I minus 2J, and you can see that it's bolded there. All right, so if I wanted to find the magnitude of W, right? I'm going to use my formula. So I have my V1 or my W1 component, which is just 1. So there's a 1 in front of I, right? So I have 1 squared plus -2 squared. So I end up with 1 plus 4, or the square root of 5. So then when I go to actually write it as my unit vector, I can say this is I minus 2J over the square root of 5. Or I could write this as the square root of 5 times I minus 2J over 5. So I did that because I just multiplied everything by the square root of 5 to get the square root of 5 out of the denominator, right? And then I end up with square root of 5I over 5 minus 2 square root of 5J over 5. So this is how technically you would write it, because this is your I component, your horizontal component is square root of 5 over 5, and your J component, vertical component, is 2 square root of 5 over 5. Okay? Makes sense? kind of like learning. It's just like when we started trig. It's like learning a new language again with vectors, right? Yep, that's what we're gonna do next, Jennifer. Actually, I was gonna do one. I was gonna try to do 46 and then maybe 52. All right. So number 46 kind of takes this concept to the next level for you. It's not just finding the unit vector, but then helping us use the unit vector to solve another vector. That totally makes sense, right? So it says, find the vector v with the given magnitude and the same direction as u. Okay, so they tell us that vector v is 3 units long, right? But it's in the same direction as vector u. So what we're gonna do, kind of to talk about this before we just jump into the math, is that we want to find the unit vector for v or for u, right? We want to find a vector that's length 1 that's in the same direction as u, and then we want to multiply by the magnitude of vector v because we know it's 3 times that unit vector. So it's kind of just adding on one little step to what we just did. Okay, so we know that u, right? U, I always want to do that. I always forget. U is at 4, -4, right? So we want to find a unit vector that shows us the direction, but that's only 1 unit. So we're just going to use our formula, right? So we're going to do the magnitude of u is basically the square, or 4 squared plus -4 squared, which is 4 square root of 2. Okay, so then if I want to find a unit vector for u, it's going to be 4 -4 over 4 square root of 2. And we're going to leave that square root in the bottom and kind of hope it drops out. So we end up with a unit vector of 1 over the square root of 2, -1 over the square root of 2. So this is the direction of u for 1 unit, right? And then we know that our vector v has the magnitude of 3. So if we know the direction, we have the direction and we have the magnitude. If we multiply the direction by the magnitude, then we're going to end up with where our vector v is. So vector v is going to be multiply 3 times 1 over the square root of 2 minus 1 over the square root of 2. So we're basically taking the 1 unit of this, right? 1 unit of this goes to this position. But we know that this is the direction, but we know that's 3 of these unit vectors. So we need to find out where that ends up. So that's going to end up at 3 over the square root of 2, -3 over the square root of 2. And then we should probably do some square root cleaning up on that one, right? And move the square root to the top. Okay, any questions about that? Nope. All right. So then let's do number 52 and 54. The last two, and then we will be on our way. Okay, so we have, in these last two, we are given the initial and terminal points of a vector, and we need to write the vector as a linear combination of the standard unit vectors I and j. All right, so for 52, just to kind of draw a quick, lovely graph here. It's a lovely graph we got. Okay, so our initial point is at 0, -2, down here, right? And our terminal point is at 3, 6. I made my graph the wrong way. Up here. That's what our vector looks like, right? So we need to, the initial and terminal points of the vector are given. Write the vector as a linear combination of the standard unit vectors I and j. All right, so the first thing we're going to do is we're going to rewrite our initial point and our terminal point as I and j. So this would be 0, -2 could be written as -2j. Okay, and 3, 6 could be written as 3i plus 6j. So if we have those two, we have our terminal point and our initial point, and we want to figure out the vector, what we're going to actually do is we're going to subtract the terminal point from the initial point. And that's going to give us the vector that we have on the screen here. So we have 3i plus 6j. So we have our terminal vector, and then we're going to subtract our initial vector. And so because we're subtracting a positive, we end up with 3i plus 6j plus 2j. This should be a j here. And we get 3i plus 8j. Okay, and so then when you look at your graph, it actually makes sense because we're traveling. It's kind of like the slope, right? Back to your slope days. We're going 3 in the horizontal, which is the I direction. And then we're traveling, if I would have drawn this right, traveling 8 in the vertical position. It's kind of like finding the slope all over again, right? So again, for 54, you're going to do the same thing. You're going to subtract the terminal point from the initial point, and that should give you the vector we have. All right. We made it through 6-3. I know that's heavy stuff, so start working through that. On Monday, we're going to talk about multiplying vectors, which is going to look kind of like matrix multiplication a little bit, kind of have this relationship, and we'll go from there. So thank you guys for coming today. I know it was a lot of stuff to get through, but I appreciate it, and I hope you have a good day and a good weekend. Thanks, guys. Bye.